All right, let's get started. Welcome to my talk from human computers to AI. The year's 2035. Jill wakes up 5 in the morning. She makes the 2-hour commute into the city. Most people in tech can't afford to live in the city centers anymore. They live in the suburbs and the outskirts. Still, Jill's one of the lucky ones. At least she has a job. As she exits the train station, she passes by the tech bros. That's what they call them nowadays, the jobless guys hanging out on the street corridors trying to peddle off-label software and NFTs to people passing by. As Jill enters the building of Titan Tech, where she works, she scans her badge and her retina. The technology Jill is working on is so proprietary it's not allowed to leave the building. The days of remote work have come and passed. The building is empty. It's a huge building, completely void of life. There's maybe 20 people working there, and they rarely meet each other. Sometimes they see each other at lunch, most times not. Even though Jill has almost a full floor to herself, she works in a very small space. It's almost like a cubicle, except it's just 8 screens that she's surrounded by. The work Jill does is mostly fine-tuning Titan Tech's developer AI. It's the AI that writes all the software in the world. Now, Titan Tech does not sell this technology or give it away. What Titan Tech does is it produces every piece of software that exists in the world. Because nobody can compete against the AI. So Jill understands the irony. She knows that she made herself and all of her colleagues redundant. And with every fine-tuning, every line of code she puts into the system, she makes herself even more obsolete. Today, Jill eats lunch at her desk. She can't stand the look of the other people's faces in the cafeteria. They're all very sad and have mostly given up on life. On Jill's desk, there's a little digital clock, black one with red numbers. It's not connected to anything. It's a remnant of how things used to be. In the afternoon, Jill sifts through new training data and commissions training data to the code factories. When 6 o'clock rolls around, she packs up her stuff and exits the building. As she walks towards the train, a police drone passes by. That's also Titan Tech technology. Everything is nowadays. In the underground, she passes by one of the code factories. Deep inside there, she sees what she thinks is Jake. Jake is an old colleague of her. They used to both be tech leads at Titan Tech. She hopes Jake doesn't see her, because at the code factories, these are the places where Jill commissions training data from. Most people that know anything about coding, this is their only employment opportunity. They sit there and they solve puzzles for 40 cents a puzzle. A guard grabs a man sitting in a computer and drags him out into the streets. That's what happens if you take too long to solve the puzzles. Jill looks down on the ground and quickly goes towards her train to commute back home. My name is Mazur, and I'm a consultant, coach, and speaker with over 20 years of experience in the industry. I used to work as a software developer, but I've been made redundant by young people. So today I work on improving collaboration between business and tech teams so that everybody else can just focus on delivering cool products. In today's talk, you will learn the abbreviated history of our profession of software development, along with all the assassination attempts that have previously been on our profession. You will learn how to prepare for the technical shifts and what skills might be required of you. And if you stick around to the end, you will also learn how you can change the future. Now, the history of our profession started a long, long time ago. It goes as long back as to the 1800s, before we had computers. at least before we had computers. So before we had computers, we had what was called human computers. Now, these were people, well, mostly women, sitting and doing a lot of the calculations by hand. And the first practice, documented practice of this is in 1875 at the Harvard Observatory, where women used to take plates of the night sky and calculate the movement of the stars. So the man who founded that practice is called Charles Edward Pickering. And he had this brilliant idea that since this seemed to be very boring and very tedious work, he could just employ women to do it, and that way he could pay them less. So that's how that practice came about. And that continued for many, many years, the manual computation of things, all the way into the 1940s and 1960s. In the 1940s, women were calculating everything from rocket trajectories to artillery trajectories for NASA and the military. They could solve really, really complex problems, and the way they did this was by taking these calculations and splitting them up amongst each other and then aggregating back the results into the final output. The reason this continued all the way to the 60s, even if we got, mechanical computers, was that while mechanical computers were quicker, the people doing the work were actually more reliable and efficient. And also, everybody didn't really trust the machines. So there's like a theme going on with that. We're not trusting in the machines. And history is messy like that. Nothing, things don't just start and stop. So even though this practice continued all the way into the 60s, we saw a new era of digital computing in the mid-40s. So the first digital computer, the discovery of the first digital computer was fueled by war. So like many historical inventions. The year was 1945 and the ENIAC was unveiled. This was the first generation of the electronic general purpose computer. And the reason it was unveiled was because there was a need for doing quicker and more accurate computations. So the ENIAC was capable of doing thousands of calculations per second, surpassing human abilities. Now, since most men were out at war, and the people who actually knew how all of these computations worked were women, the people programming the ENIAC were still women. And the way this was done, the way the programming of an ENIAC was done, was by using these manual plug boards and switches. So to input a new program, you had to physically reconfigure the whole computer. Then inputs and outputs were mostly done on punch cards. Later we got the EDVAC, which was the first computer that introduced a stored program architecture, which meant that the input and the program could be read in the same way. Now, this changed everything because this meant that you could switch programs much quicker. Now, still, the programs were done mostly on punch cards, and mostly on punch cards. But with this introduction, what happened was that programming went from like a configuration task to an actual creation of the program. So even though now we were programming, we were actually doing programming, much of it was still this binary language or assembly language type of programming. This meant one thing: it was really, really hard to do. And secondly, it was machine specific. So if I made a program for this type of machine, I couldn't bring it to another type of machine because all the programs were specifically tied to how the hardware was built. Now, these two things were a huge industry problem because neither programs nor skills were transferable from one computer to another. So enter the era of programming languages. Now, the first major breakthrough in programming languages was Fortran. So while Fortran was considered a more modern language written with instructions and compiled, it was still largely done with punch cards. The second breakthrough came with Grace Hopper, a woman that was part of the UNIVAC team, which was one of the first computers for business purposes. Now, Grace believed that computers should be given instructions in plain English. So she pioneered many of the ideas which later became modern programming. Eventually, her ideas led to COBOL in 1959. And with COBOL came, well, you guessed it, with COBOL came the first assassination attempt on our profession. So because there was this huge rise in demand for business software in the 1960s, it was the first time the idea came about of replacing all of these pesky computer people with, something else. And with COBOL, a language that was designed to express programs in business language, and it almost read like English, came the idea that maybe we can democratize software development and cut out the middle person. The reality, well, writing COBOL programs was really hard, and it still required deep technical knowledge of both the machines and the programming languages. So who would have thought that that would actually be the case? So instead of eliminating programmers, what happened was that there was this massive surge in demand for COBOL skills. Now everybody wanted skilled COBOL programmers. So this is how we made it through the first assassination attempt on our profession and actually emerged stronger at the back end. Now, the next thing that happened was actually that we got our first label, right? Because up until this period in time, programming had been something that, it'd been a skill, like people did it in their jobs, but as an add-on to other things they also did. So this is Margaret Hamilton, and what Margaret Hamilton worked on the Apollo 11 project, and she wrote code for the moon lander. Hamilton had an engineering approach to programming and development, and she wanted to professionalize the skill set and have it taken more seriously. Now, she recognized that software was usually seen as an afterthought, like something you kind of put onto the hardware. But she wanted to make it a legitimate process and profession. And she did this by coining the term software engineering, as a contrast to hardware engineering, which was more prevalent back then. In the beginning, this wasn't really taken seriously. A lot of people made a lot of fun of it, as she's attested to in interviews. But eventually it caught on, and now we had a label. Now we knew what we were. We were software engineers. So this did lead to a professionalization of the craft, which is really important, because when you professionalize something, you also create a discipline around it. When you create a discipline around it, you create ways of working, you create a shared knowledge, you create things you can study and talk about. So now we knew what we were. And this rapid and chaotic growth of software during the 60s and 70s led to something else. It led to something that was coined the first software crisis by Dijkstra. And the issue was that the things that we were doing were really, really hard to do. And it was specifically hard to do them correctly, especially when trying to build these large-scale, reliable software systems. So quality was poor, budgets were overrun, and deadlines were missed. I'm not talking about today. It was this was in the 60s and 70s. But I guess not much has changed. So Dijkstra coined this term, the software crisis, and he said, as long as there were no machines, programming was no problem at all, and now we have gigantic computers, programming has become an equally gigantic problem. And because of the crisis, we saw the beginning of what we today call software development. So in his speech, the humble programmer Dijkstra addressed three things to solve the ongoing industry crisis. One, he had a call for structured programming, which meant you need to keep your code clean and well organized. Secondly, proof of correctness. This meant that you needed to mathematically prove that your programs to be correct. A big part of this was having a specification, knowing what correct actually meant. And the third one was abstractions, meaning breaking down the large and complex problems into smaller bits and pieces that could be more easily managed. So this was the beginning of the formalization of the craft. These ideas have inspired everything from design patterns to architectures to ways of working. And it all happened because we created a big mess, a big ball of mud. So, of course, things didn't get better overnight, but over time we managed to figure things out. And the next significant impact on software engineers actually came with the introduction of a new technological marvel, the microprocessor. Now, this was a very compact, affordable circuit that contained the functions of a CPU. Up on this time, it was unthinkable to have a computer in your house. You had to go somewhere to use a computer, which was usually your job or a university. Now, this drove the price down, and it was now possible to have these computers in your house. The first microcomputers were sold as kits, meaning you ordered them online, or not online, sorry, online. You ordered them, and you got them home, and you had to build them yourself. So these were mostly used by hobbyists, right? People that wanted to geek out around the technology and figure out how it worked. And you really couldn't do that much with one of these kit computers. Now, with the emergence of microcomputers, we also got some non-kit computers. This picture is from a French company called R2E, and they developed and sold the Micral N, which was, I think, was one of the first non-kit computers to be sold. It never became a big thing, but they existed. Now, instead, the big thing became the US Altair 8800. That is a hallmark of the era. However, there was like one big issue with the Altair. When it was delivered, and this was a kit computer, so you had to build it. It contained no operating system. It required machine language to be entered manually. And over time, of course, it improved. It did get an operating system. But because of this, you needed to know a lot about computers in order to use the Altair. Now, the big shift really happened with these two gentlemen. And what they did was they just made stuff up. Like, they just promised things they didn't have. So this is Bill Gates and Paul Allen, also known as Microsoft. Now, they saw that microcomputers required a structured way of programming them. So they told MITS that they had a version of BASIC, which was a prominent programming language then, running on the Altair. And MITS was like, yeah, cool, could you come demo it? The problem was that they didn't have a functioning version of BASIC running on the Altair. They didn't even have an Altair. So they had a friend who helped them build an emulator for another computer that they actually had. And then they built the BASIC inside of that emulator. And then went to demo it to MITS, and this is the part I find unbelievable about this story. It actually worked. The demo actually worked. The demo never works. That's like a rule of software development. So by some miracle, it actually ran. And Microsoft BASIC became the de facto standard, shipping with several different computers. Programming was now something that was not only isolated to the professional programmers. programming now became for everyone. Everybody having an Altair, having Microsoft Basic or any other type of computer that ran Microsoft Basic could do programming. So now it was not only for business applications and space programs and wars. Now it was for fun and games and everything else. This laid the foundation for the modern software industry as we know it today. Now, with this, of course, there had to be another assassination attempt on our profession because we were getting too powerful. So in came the promise of 4GL languages, fourth generation languages. Now the idea of 4GLs was simply that we would make it very, very easy to program and thus reduce the need for professional developers. The approaches of the 4GLs were slightly different depending on which language you looked at, but the whole idea was to enable non-programmers to create powerful programs and make applications. So the prediction was that 4GLs would completely democratize software development, removing the need for developers. The 4GLs were supposed to enable business people and business professionals and domain experts to create the applications on their own. The reality was that the 4GLs were not very flexible, they were slow, and they were still pretty complex to handle. So it didn't really work out the way they expected it to do. And then the growing need for more complex systems and then the exponential growth in technology again helped us dodge another bullet. And not only that, it launched us into the golden era of software development. Because the 80s marked this rapid growth and innovation in our industry. So this was mostly fueled by the entrance of the personal computer. First with the PC in 1981 and then the Macintosh in '84. Now what the personal computer brought to the scene was it brought computing to the masses. This created a high demand for all types of software. Because the user-friendly environment and interface of the personal computers meant that not every consumer of software needed to be a producer of software. You could actually use a computer without understanding programming or without knowing how to program or for that matter knowing how the computer functions. So now all of a sudden we had an industry which had an imbalance between consumers and creators. So the demand was really high. In this era, we also got new languages and new IDEs. We got Pascal, we got C++, object orientation came on the scene, and companies like Microsoft, Apple, and Lotus really took off. But this also sparked the first idea of what I say would be considered a software developer, to contrast that with a software engineer. Because all of these abstractions and technology allowed engineers to move from simply being the builders to being the creators. Meaning that they would not only build and craft the programs, they would also come up with the ideas of what the programs would be doing. Developers were not only making software, they were inventing it. They were solving the user's problems with the technology that they had at their hands. New skills came on the scene like design, business thinking, project planning, and the profession became much broader than it had been previously. Developers were doing so much more than just coding now. So the 80s really formed a profession to much of what we see today. And just as we thought it couldn't get any better, we came on to the second golden era of software development. And this came with the emergence of the internet. So Tim Berners-Lee decided that it would be cool if there was a better way for computers and people to communicate with each other. And he created the internet. With the emergence of the web browser and HTML, the demand for software developers skyrocketed. Now everybody was launching the next internet product, the next cool .com startup. We saw emergence of e-commerce. Companies like Amazon and eBay came on the scene, which meant that our skill was in really, really high demand, and we got a bunch of new colleagues. because now all of a sudden, all the ad agencies and print designers were becoming web bureaus. And with that, came the third assassination attempt on our profession, probably the least serious assassination attempt that was ever made. This was the what you see is what you get editor and the Flash Macromedias of the world. And the only reason people tried saying that it would kill software development was because they didn't understand what we were actually doing. They didn't understand the complexities of the profession because they thought everything was just about building web pages. Meanwhile, we were focused on things like databases, UI, UX, but also psychology, because the name of the game in the 1990s was eyeballs. We wanted to attract as many eyeballs as we could to the websites, because we measured success in eyeballs, not in money. This was also the downfall of the whole dot-com era, because all of a sudden, the investors that had poured bunches of money into all of these websites came back and said, like, hey, where's our return on all this money we gave you? And you can't really monetize, or you couldn't really monetize eyeballs, so it all just came crashing down. And with this, we as professionals stood up and we swore that we would never build dumb shit without customer value again. No, we didn't. But it would be cool if we did. We did try. In comes agility or agile. So with Agile Manifesto, as a direct response to all the heavy ways of working of the software industry with the project plans and the Gantt charts and the requirement-heavy work, that didn't really meet customer needs. Now, for me, with Agile, a big thing was the shift from thinking about doing the work to thinking on delivering the value. But as we saw the emergence of Agile and these new ways of working, this also meant that we needed to start seeing our job differently. So with all of this, all of a sudden we now had to do things like clarify user demands and customer needs. We needed to negotiate our work, plan, design, in addition to building things. We needed to coach teams and grow our own skill sets because there was this huge emphasis on the continuous learning, continuous improvement. So software development now was a far cry from the computations that we were doing by hand in the beginning. So over this time, we just kept building these abstractions on top of other abstractions, meaning we got further and further away from actually doing the technical work into creating software. Now, I only have two more things here before I'm going to move into what all of you want to hear about, which is the AI part of this talk. Now, the next thing, even though it technically didn't change the profession, it did do a huge impact for our industry. And this was with the emergence of smartphones. Now, imagine that today, more people own a smartphone than people own a toilet. So with this huge explosion in devices that demanded to be filled with content, filled with software, also came a huge surge in demand for skilled software developers and skill set in order to build all of that stuff. Now, I live in Sweden, and I imagine it's similar in Norway. You really can't do anything. Everything from travel to banking to planning to communication is done through your smartphone. You probably, in the first 2 hours you wake up, interact with like 10 to 20 pieces of software just in your phone. So it maybe didn't change our working conditions or what we do every day, but it did really shape the demand for our profession. And the second modern day technology that impacted us was the introduction of cloud. Now, in the early days of cloud computing, there was a lot of jokes going around. It was like cloud is just, running your stuff on somebody else's computer. Ha ha, very funny. The thing is, we didn't really see back then what cloud would become now. We didn't really see what it was going to be about. Because the value of cloud was never the hosting part. It was never that I can outsource my hosting to somewhere else. The value of cloud, just like with early day computers, was the abstraction part. We abstracted away the complexities of what it meant to run scalable software. With product as a service and cloud native applications, we could now leverage already built components to do really cool stuff and accelerate the creation process. We had to focus less on the plumbing and more on creating the value for the users and the customers. Again, we shifted further away from our technical role and more into that role of the creator or the problem solver. So, now the code we write is even less plumbing and very much focused on doing these novel things that haven't been done before, to solving those business problems that haven't been solved before. And this brings us to 2024, the 2020s. So, it's safe to say that in the 2020s, the significant technology that everybody's talking about that's probably going to impact our profession the most is the generative AI. And specifically, when we talk about generative AI, we talk about its implications on productivity, in our context, developer productivity, but in general context, the productivity of many professions. So of course, we could view this as another assassination attempt on our profession. We now have generative AI, so software developers as we know it today are going to become redundant. Now, here's some numbers from a study conducted by GitHub. So what GitHub did is they took about 90 developers and gave 45 of them Copilot and 50 didn't get Copilot. And they gave them a well-defined task to solve. Now, with Copilot, 78% of the developers managed to finish the task. Without Copilot, we have 70%. That's almost the same. What's interesting was the average time to task completion. So with Copilot, it only took 1 hour and 11 minutes, but without Copilot, it took 2 hours and 41 minutes. Now, what's relevant to note, if you actually go and read this report, is what the task actually was. So the task was actually to write an HTTP server in JavaScript. Why do I think that that is relevant? Well, because there's plenty of HTTP servers written in JavaScript, so the training set for HTTP servers in JavaScript is really large. So the suggestions you're going to be getting in solving these problems are going to be really good. But still, hey, it's a 55% productivity increase. We have to acknowledge that. We have to say that that is pretty impressive numbers. But what's also curious about this is there's another study also done by GitHub, which means that depending on the seniority level of the person using Copilot, the accepted suggestions significantly drop. So with the seniors, they only accepted suggestions, the seniors accepted suggestions 27% less than the juniors. Meaning that you get less value from the tool if you are really good at what you're doing, or maybe you think that the suggestions the tool is providing aren't that good if you're really good at what you're doing. But if you're less experienced, well, from your frame of reference, the suggestions become really good. Now, all right, so we have this 55% productivity increase in the coding, in the actual solving of the program. What's interesting to me now is how much time do we actually spend coding, right? Because a 55 productivity increase in coding is only relevant if we look into the time we spent doing the actual programming. Now, these numbers come from a survey. It's a self-assessment survey done in a study with roughly 1,200 developers. These numbers are specifically for people that self-identify as software engineers. Now, first thing that surprised me here is that there's no slice called meetings, which I think should be there, but I'm guessing they grouped that into administration or brainstorming collaboration, depending on what type of meeting you were having. But still, it's almost 50% of the design and coding. That's not too bad. So we spent 46% on designing and coding. But then there's of course this other slide, which is waiting for tests and builds. And there's only one thing. There's only one thing I can show you in regards to that slide, and I have to show you this, which is classical XKCD. Number one programmer excuse for legitimately slacking off, my code is compiling. So I wasn't satisfied by this. 46% designing and coding, what does that really mean? So I did find some other data on how coding really looks. So from the 46% on the previous slide, now I'm doing horrible stuff here. I'm smashing surveys together and different reports, and I'm well aware of what I'm doing. But just this is a mind experiment. What coding really looks like. So this is a study done by using software on people's tools, on people's computers, measuring what they actually do on the computer. Now, this study only looked, and this is very important, it only looked at 18 test subjects. So this is 18 developers over 740 coding sessions. A coding session is a stretch of uninterrupted time which was spent at the computer, so it's not a full working day. Now, 1/3 of these test subjects were professional developers, and the rest were students varying seniority levels, all the way up to PhDs and all the way down to bachelor's students. Now, 70% of the work is actually understanding. So 70% is actually just sitting and trying to figure out, what am I looking at? And what am I supposed to be doing next? I don't know if this is affected by the fact that this study was done in Smalltalk, and that maybe takes a little bit more understanding. But they do claim to have similar numbers in Java. I'm not going to comment on that. But I think the point is clear. The actual writing of the code is not the part that takes up the majority of the time. It's the thinking part which takes up the majority of the time. I did also find this data, which was interesting, and this is data which has been gathered globally by a company that builds a tool that people voluntarily install on their computers, which measures how they use their computer. And this data set is huge. It's based on 250,000 individuals, 250,000 developers that use this tool that records their activity voluntarily. And it shows that the median developer only programs for about 47 minutes per day. That accumulates to 4.5 hours per week of actual programming. Like the most code-intensive people here, the 1%, do 4 hours and 20 minutes per day. So, given all of this, if we see this 55% productivity increase in coding, what does that actually mean? Well, I'm going to do some assumptions. Given all of these numbers, I'm going to assume that say we program somewhere between 2 to 4 hours per day. And the rest of it is spent in thinking and meeting and designing and waiting for code to compile, so 2 to 4 hours. So I have 55% productivity increase. Well, that means you get 1 to 2 hours of additional work per day. Now, is anybody in this room not able to fill 1 to 2 hours of additional work per day? I'm looking for, no. So most people in software are going to find things to do for the 1 or 2 hours additional per day. Because the skill of a software developer is not only about coding anymore. Of course, we have the programming, we have the testing, we have the security, infrastructure, systems design, architecture, domain modeling, all the development practices, the problem solving. There's so many things we do that go into our profession beyond the actual coding part, beyond the actual programming part. So now we work in these cross-functional teams and product teams. Our job has not been to code for a very, very long time. Our job has mainly been to understand and to model reality in a way that it makes sense. Like most of us, we understand the businesses we are working for better than the business people understand the businesses we are working for. Because we need to take those things that they say and make them make sense in a way that we can codify it into a program, into working software. So our job is to take user problems or customer problems and apply the latest technology to those problems in order to create cool programs and cool products that the users love. So that's the historic shift. Our jobs with time become less and less technical, and they're even less technical today for the vast majority of us. So with that said, let me give you another story from a different one from the one I told you in the beginning. So the year is 2035, and the sun is shining over the bustling city. Jacqueline slept in today for no other reason than she could. It's around 10 when she leaves her central apartment and strolls down to the Creation. The Creation is a co-working space where Jacqueline and like-minded creators meet every day to share ideas. As she strolls past the city square, it's filled with people. So the high level of automation in society has created an economy of abundance. Most people don't work or only work very little. Some, like Jacqueline, they enjoy bringing new ideas to life, passion projects. Some of them are sometimes profitable, some of them are helpful. Today is a special day because Jacqueline has had this idea that she's been working on in her mind for weeks. And just before she went to bed, she set all her AI agents on creating the idea. And when she woke up in the morning, the code was done. She hasn't run it yet, but she's bringing it with her into the Creation. It's supposed to be an XR application that is a time machine. It can take you back to any time in history. As Jacqueline enters the Creation, there's a bunch of people sitting around the old tree. That's a tree in the center of the building. That tree has been there for thousands of years, way before they built the building. Now, she grabs Mila and Kostas and goes like, hey, I want you to experience this with me for the first time, and drags them into one of the XR rooms. She loads up the application, taps her smartwatch, and the hollow projector in the ceiling just changes the whole space into the 1960s. Their clothes have changed, the furniture has changed, the whole vibe has changed. There's even music from the 60s playing in the background. All of the three of them are really impressed. This is Jacqueline's third product this month. Now, a lot of the products that Jacqueline creates never see the day of light, but some of the products she's built have thousands of users and are actually filling really cool needs in society. Now, the three of them decide that the best way to figure out what to do with this whole new idea would be to go for a beer lunch. So they exit the Creation and go to their favorite pizzeria for pizza and beer. Now, this scenario has one thing in common with the previous one I told you. It assumes a very high level of automation of developer skills. It assumes that we can reach to a level of AI where we can simply tell the AI what we want and it's going to do the job for us. Now the question becomes, what if we can't reach that level of automation? What if we can't get there? Now, This is something called scenario planning. So we have high automation on one scale and low automation on the other one. And then we have restricted access to technology versus accessible, meaning there's free access to the technology. Now, the first scenario we talked about, this is a high automation restricted scenario. This is a scenario where we do achieve a high level of automation, but the technology is restricted for use. Restricted can mean owned by one or a few companies, but it can also mean restricted in the sense that we can't run it. We don't have enough computer power or energy to run it, or the consequences of using that amount of computer power or energy are devastating to the planet. So it's just not freely available. Now, this scenario is the age of the elite supervisor, right? Because there's this elite that has access to the technology, and then there's everybody else. The second scenario we're talking about is still a high automation scenario, but it also assumes that the technology is accessible for everyone. It's accessible for everybody to use freely and accessible for everybody to do with what they please. So this creates something else. This is the age of the digital creative, because the focus now becomes on ideation. What can we conceive? Because the building is not a problem anymore. But there's also two other scenarios here. There's also this scenario, the scenario which I call the software worker. In this scenario, we don't manage to achieve high automation, so the reliance on people operating the technology is still high. However, the technology is restricted. It's owned by a selected few. It can only be used by a selected few companies or organizations. Now, these organizations have the advantage over everybody else trying to build something. The result becomes that if you want to create a piece of software, you're most likely to contract with one of these organizations that have the technology to build the software in the fastest and most efficient way. So most jobs are now found inside of these restricted organizations, making them able to drive down the wages of the software operators or the software workers. Maybe you're paid by the ticket or by the task. Work is planned somewhere else. You're not really involved in the problem solving anymore. And we've achieved perfect Taylorism. We've achieved the software factory. Other jobs will exist. There will be the artisan software development shops, just like there's craft beers out there. But these will be like the Carlsbergs and Heinekens of the world. So this is the age of the software worker. We've basically been reduced to industry workers. And then there's the fourth scenario with accessible low automation. This is basically where we're at today. So this scenario is most akin to the way we work with Copilot and other automation tools today. We have automated software creation and are happily working together with the AI. There are our assistants. The technology is accessible for everyone, meaning that there's a level playing field. We don't see the difference between the haves and the have-nots that we've seen in the previous scenarios. However, we do spend more time on different types of tasks than we previously have. Maybe we spend some more time on creative thinking, on ideation, on looking at the code. So this is basically an extension of where we are today. This is, the second age of software craftspeople, if you will. So I don't claim to know what's going to happen. I don't even know if these are the correct axes to do the scenario planning with. But this is a tool you can use in order to make your own scenario planning, to figure out what you think about the future. Because once you've done this, you can start mapping out the skill sets needed to manage these different types of scenarios. For instance, in all of the high automation scenarios, we're going to have the skill set of supervising the technology. You need to know how the technology works, and you need to be able to supervise whatever it's doing, the same way we're supervising machines in other automation scenarios today. You're also going to have ethics, because machines don't have ethics, so that falls on you, the skill set of knowing what's right and what's wrong and how do we apply the technology in a better way. While in the scenario of restricted and high automation, well, if you want to have a job, you should probably look at AI and data science, because the few jobs that will be out there inside of the field will be all locked up inside of AI and data science. While over here, it's more about creativity and innovation, because we have the tools to build whatever we can dream about, but somebody has to come up with these cool ideas. On low automation, we still need systems design. We need to be able to design the systems and build them, and architecture, these types of ideas, because we can automate some of the creation, but like the bigger part of the function of the system still needs to be done manually. And in the accessible low automation scenarios, we still need to read and understand the code that's being generated. We need to know that whatever was generated is the correct stuff being generated before we allow it to go into production. And over here, it's a lot of classical programming, because not everybody's going to have access to the technology, and if you don't have access to the technology, you still need to have some classical programmers, so being good at programming over there is still relevant. Here, a lot of interpersonal skills, because in the accessible scenarios, we have more a collaborative approach to things. We work on stuff together, while in the restricted scenarios, well, we can imagine it's more a classical project management type of skill sets. So these are just all examples, but this is a very useful way of kind of thinking about the future, or kind of trying to break down the future beyond the hype articles that you read, that software development is dead. Now you can do your own scenario planning, you can plant your own axis, and you can create your own stories, and then try to figure out, if this is the future I believe in, how do I place myself inside of that future? So, with all that said, as you leave here, what should you do? Well, the first thing I want to leave you with is that I recommend everybody to make their own bets. And I prefer saying bets to predictions or theories or assumptions, because the way I view a bet is it's mix of data and gut feeling. So we have this incomplete data, but then we have a passion and a belief in what's going to be happening. I'm not big into sports, but I imagine if you do sports betting, you have your sports team, and there's some data around, some odds around what's going to happen in the game, but then you also have your belief in what's going to be happening, and that's the way you place your bets. And then as the game progresses, new data emerges and different things happen. And while you can't withdraw a bet, you can always make a new bet, right? So you can always bet on something else. And this is what I mean by taking bets. Because we take one bet today when new data emerges, doesn't mean we can't change our minds and make another bet as we go forward. We might have lost some time or money or something, but that's just the way it goes. The second thing I want to leave you with is that you actually work in this industry, which means that you can tip the scales of where we're going to end up. You see, when technology is open, it creates a lot of opportunities. We saw this for people that saw Dylan's talk this morning. When we have open technology, there's opportunity for a lot of people to get involved and contribute and do cool things. We saw this with the internet. If the internet would be proprietary, it wouldn't have had the same effect on society as it had. While when the technology is restricted, like the mega computers were, when you had to go to companies or industry or universities to use them, that creates a divide between the haves and the have-nots. So when it's closed, stuff becomes pretty miserable. When it's open, it creates a lot of opportunities. Now, all of you actually do have the power to tip the scales. I mean, even if you don't have the power to do it yourself, you always have some level of influence. The way you express yourself, the decisions you influence or advise on. So, if you are fighting for a cause, let it be the free access to technology. Free access to technology. So with that said, the future, it's not written yet, and you can change it. You can affect how things will play out. So go out there and make the future you want to have. Thank you.